Recording is rolling. So welcome to Friday. You guys have just turned in your Chapter 4 homework. You guys also remember that AP Classroom Unit 2 multiple choice due Monday back from the weekend, so that I can go over that then. Oh, you guys got federal impact forms. You guys see those on your desk? Federal impact forms? So take those home, bring those back. The due date is officially 1 week from now on Friday, but well, if you turn in earlier than that, then I will definitely take those early. So sometime in the next week, bring back federal impact forms. Did you guys write that in your planners? Federal impact forms? Right after AP Classroom Unit 2. Got you guys, your kinematic quizzes are back. So I handed those out. Those were on your desk when you guys walked in. And the solutions I posted to Google Classroom this morning. So if you want to do corrections, then, well, the solutions are out there. So you guys can do corrections if you want for half credit back. Also, I have for you guys your next Open Notes take-home quiz. This is your dynamics quiz. Oh, it's clipped to the front of your desk. Okay. Not the right side, the front. It's clipped to the front. It looks like this right here. It's got some free body diagram setups on one side. It's got some AP level questions on the other side. You guys see those? Right, so Open Notes take-home quiz, that is due 1 week from now. Next Friday. You guys got 1 week for an Open Notes take-home dynamics quiz. Those are some pretty tough questions. So actually, I do want to help you guys out on a couple that, well, showed up on the bonus homework, but hadn't quite explicitly gone over class. I'm sure a lot of you guys can figure these out, but just to give you guys some heads up. Number 9 and number 11. These two setups here are involved in those. So let's go over those real fast. Got one question. What is the average force on a ball bouncing it off a ball? Boing? What's the average force on that ball? Now, if you look at the setup, you guys can probably imagine, well, force, something to do with the mass of this ball, is probably going to feed into Newton's second law of motion, which is true, but you sketch this out and show you guys some pointers. So here's this ball, you throw it at the wall, it goes boing, bounces off. I'll call this V throw and V rebound. This ball has some mass, called M for mass. And there is one last thing you have to know to get the force from the wall, and that is the time of contact with the wall. So I'm going to call that delta T. So delta T represents the time interval. It says like change in time, but okay, we'll call that. So delta T, time interval, okay, of contact with the wall. Now this would be a very small fraction of a second, wouldn't it? If it's just boing, maybe like some number of milliseconds, something like that. Well, I'm going to make up some numbers, maybe just to help you guys out a bit. Let's say you throw the ball at the wall at 20 meters per second. And the ball rebounds at, can the rebounds be more than 20 meters per second? Or the throw speed? No. Unless maybe the wall is moving, but if the wall is just stationary, which most walls are, then let's call it 15, I guess, meters per second. I'll make up a mass of the ball. Maybe like this many kilograms. I think it's pretty close to a baseball. Okay. And let's say that the time interval is 50 milliseconds. So it'd be 50 over 1,000 seconds, like that. What is the force? What's the force? I should say, what is the average force? Talk about that a little bit too. So the average force, force average. Wouldn't this be Newton's second law of motion? F equals ma. So that's the mass of the ball times acceleration of the ball. And there's one place where the ball is definitely accelerating a whole lot, and that's when it's in contact with the wall. Okay? So I'm going to rewrite acceleration in terms of your kinematic information. This goes back a few weeks ago. F average. I mean, one way to think about acceleration is, well, Newton's second law of motion, but we're doing that right here. So wasn't the original way that I taught you guys acceleration a rate change of velocity? Wouldn't it be change in velocity per change in time? Isn't that what that is? That's it. Good so far?
Good.
All right, now, as long as you can figure out what's what, then you'll be good to go. Like, hey, the mass of the ball, that is that number right there. Okay, so that's easy. Check, done. The time interval, that's, well, that number right there. So, check, done. but that feeds right in there. Okay. And now here's the tricky part, and this is the main reason I actually bring up this problem at all. Okay. Change in velocity. I wonder how many guys are going to get this. If you throw the ball in the left direction at 20 meters per second, and it rebounds in the right direction at 15 meters per second, guys, what is the difference between 20 to the left and 15 to the right? And it's not 5 meters per second.
-35.
Who said 35? Yeah. Juliet got it. 35 meters per second. So I'll draw a number line, and if you didn't see it before, you're about to definitely see it here. So 20 meters per second to the left, maybe there's like an implied negative sign on this. So there could be like -20 meters per second. Let's put 0 meters per second here, and then 15 meters per second. That's approximately the scale, right? I bet you guys definitely see it now. You guys see the difference between this and this is 35 meters per second. That is what this number is right here. It's 15 minus -20, which is, of course, 35. Okay. All right. So you guys ready to field a bouncing ball question? Bet you guys could do that, right? Actually, if you did the bonus homework, there's one that's pretty similar to this. It involves the dropped ball, so there's like a couple of extra steps, but it's same premise. Okay. And then the other one I wanted to mention is pulling a crate. Notice this guy is pulling this crate with a tension force that's not horizontal. It's up a little bit, right? It has a vertical component. And again, I bet probably most of you guys can figure this out anyway, but we haven't actually explicitly covered something like this in class where the normal force on the box would not be equivalent to the weight of the box. That's usually been the case, right? Usually the normal force is equivalent to the weight on a level surface. Now, your quiz question is not exactly this, but this would be a middle step that you have to do. So let's set this up in, let's look at a free body diagram for pulling a crate up at some angle. So free body diagram. Try to make sense of this. So this block has a weight. Pull it straight down. Call that mg. Start over. I want to make that a really big vector. I want to make this really obvious what's going on. Really apparent. Alright. So free body diagram. This thing a big old weight. mg. Yeah, there we go. Now what? Tuck in. Introduce a Cartesian system. At least I'll get this axis going. Because see, someone's pulling with a tension that's kind of up and to the right. Like some tension T. Right? Maybe you got those forces, and then there's also a normal force, right? But what is the normal force equivalent to? Well, it usually did. Like if I'm not pulling on the box, if you just had that going on, then the normal force would be mg, wouldn't it? I guess that's balance it out. The key is this. The key is that the sum of the forces in the y direction must be 0 newtons, right? Because the box should be in equilibrium in the vertical direction, right? The box can't be accelerating up and down, right? And this condition so far is usually led for the normal force just to be equivalent to the weight. Right? But if you're pulling kind of up-ish, say at some angle, isn't it true you're somewhat alleviating some of the force from the floor? Right? Like if this box was sitting on a bathroom scale, here, there's like a bathroom scale down here, this box is sitting on, then when you pull kind of up-ish, doesn't the scale rating go down a little bit? I wonder by how much. Right? Well, let's split this tension into components. Where this is T cosine theta, and this is T sine theta. Is that? No, there's definitely a normal force, but I was saying it was not going to be equivalent to the full weight. Maybe it only goes to about like that much, call it normal force. And the question that I threw on the setup here was, well, what is that normal force? What is that normal force? Now, if you set up a full equation and then go solve for a normal force, you'll get what I'm about to write. So I'm sort of skipping stuff and just. So you start with this. So this force up plus this force up plus this force down has to zero out. Okay? And then if you do some algebra switcheroo and solve for this, wouldn't this just be the difference between the weight and T sine theta? Okay. So it's that minus that. Okay. Does that make sense why that would be? Guys get it?
Could you show the original question again?
Yeah. The original question was, this guy's pulling a crate across the surface, but he's pulling up at some angle. what is the normal force on the box? Okay. Actually, if he pulls too hard or he pulls at too great an angle or some combination of those, isn't it possibly he might even lift the box off the floor, in which case the normal force would just go to 0? Okay. That could happen. I didn't set the quiz question up to do that, but could happen, right? If he pulls too hard at too great an angle. Okay. But in this free body diagram, it partially relieves that normal force. Okay. So do you guys see that this vector plus this vector adds up to this vector? I tried to draw it kind of like that. So this plus this should add up to this. Okay. Is that? So that it zeroes out in the y direction. All right. I wanted to clean that up before you guys took off for the weekend. But now the main thing for today. Well, originally I was going to do an FRQ with you guys, and then for my honors class, I was having put together a very known frame, and this actually ended up being so cool. I want you guys to do this too. You guys can get your hands on some lab equipment, like these pulleys. So what is this? What's this about? Let me switch my screen over and show you what the premise is. So share screen 2. Ooh, a map. Hey, looks fancy. I think that's I think it's the Netherlands is what that is. Let's scroll back to here at the beginning of this video. So you guys are about to solve an economics question today, an economics question using physics that you guys have pretty well seen in this class with lab equipment that you also have been familiarized with. So the economics question is, where should you locate a factory to minimize transportation costs? Right? Suppose that maybe you're trying to construct, you're trying to make something in this factory. The slide you guys are looking at right now has 3 inputs, right? Inputs 1, 2, and 3. On the paper that I'm about to give you guys, I'll just narrow that down to 2, make it a little bit simpler. But you got 3 inputs, and then you're going to make some product in the factory, and then you'll have a finished good that you want to ship to, like the market center, maybe like a town, something like that, right? Now, if the transportation cost is the same for all these objects, or all these inputs, and also the finished product, then you probably want to locate the factory probably pretty centrally located, right? That would minimize the distance and then therefore minimize the cost. But that might not be the case. It might be the case that maybe it's like really expensive to transport this material here. Maybe this is like wood. Maybe this is like copper up here. Maybe it's really cheap to transport the copper because there's not very much of it and whatever we're trying to build, something like that. Maybe we're trying to build pencils. Right? So we're trying to build pencils. So the pencil, we got a wood part, we got a metal part, but there's not very much metal, but there's a lot of wood. So that's going to be pretty expensive, pretty heavy. Okay? So whatever it's really expensive to transport, do you want your factory really close to that or really far away from that? Really close, so that you don't have to move that very far, right? So that could like minimize the cost, right? Now, if you know the transportation costs like per unit, and then like per kilometer, and you know some trigonometry, then you can solve this on paper with just a bunch of fancy trigonometry in physics, but that would take a long time, right? There is a very fast physics solution to this, and that's to set up a very known frame. And what you do is you represent the per unit transportation costs as lab weights, right? So it'll be proportional lab weight. And see those dashed yellow lines? You replace those with physical string, and you have all the strings tied together at the middle. And well, scroll later to this video. There's Mr. Very Nolan himself. It's got a random G in his name. Guess he's French or something. And hey, look at that. You see like a metal ring down here? And there's some strings emerging from that. That's where all the strings are tied together. So there's the location of the factory. Let's get a more macroscopic view of this. Oh, there's like a pulley. Now you guys have red ones, but other than that, it's like the same thing. You guys have some pulleys. Right? You guys got some lab weights. And then what's this look like? Right. So I see the pulley. Now each of those pulleys could represent one of those locations. It might be the forest or the copper mine or the town that you're shipping everything to. Right? And see that factory right in the middle? Okay. Right. And there's lab weights that, remember, the mass of each one, the weight of each one is proportional to the transportation cost. Right? Now watch what happens when we put this in motion.
From the side, it looks like this.
See how you added some weight on the right side? Let's see, instant replay. Let's go back a little bit. Okay. So here's the factory here, and then those weights are pretty equalish. Okay? But he's gonna add more weight. And you guys said if there's more transportation costs, you want to park the factory closer to that point. And watch what happens to the factory. See how it naturally reaches a new equilibrium point? That solves the problem, right? So without any paper trigonometry, it just solves it with physics and equilibrium, right? Oh, change the weight again. The location, equilibrium location of the factory keeps moving to wherever that would be. Right? Here's what it looks like from above. Right? Yeah. So you guys, there you go. And then as you change out the weights, then the economically
So it's like the most
most
optimal
efficient.
place.
Yeah, optimal. That's what I was looking for. Optimal place to park that factory. Yeah. Well, I'll find it right there. Right. So how does this correlate with, say, like some kind of lab paper I could give you guys? So switch back over here. Right, so now my printing budget's getting pretty low, so you guys gonna have to share these. You guys can put several names on a paper. I've got 3 scenarios. I've got an example scenario. I've got scenario A and scenario B. Okay, so we'll start with and you guys see they're all kind of like the same format. So let me go through this example scenario so you can see exactly what numbers go where and where everything's coming from. So you need to know the transportation costs. I mean, that's part of the premise of this. So again, we're trying to build pencils. And let's say these pencils only are made out of 2 things. We got the wood and we got this metal thing. I guess these pencils can't write. I guess that's an oversight, but never mind that. So wood and metal stuff. So there's, let's see, transportation cost of wood, which is probably coming from a forest. Okay. We got transportation cost of copper, which is coming from a copper mine. And then once we build the pencil, we'll have the finished good. There's the transportation cost of the pencils. And that's being sent to a town, right, where people can buy the pencils, something like that, right? Now, in my example, I made the transportation cost equal. So just, you might represent that with equal lab weights. Maybe like 100 grams, 100 grams, 100 grams, something like that. Right. And also I give you guys coordinates of each of these 3 locations. So here's the forest at 0, 0. The copper mine is, what's up with these numbers, like 0, 1, 22? I can tell you why I chose those numbers. Because, we back up here, as it turns out, the width of your lab table, this black lab table's back there, happens to be exactly 122 centimeters. So the width of this lab table, 122 centimeters. So let's see, where would the coordinates go in my example? So the forest is parked at 0, 0 in my example. So here's the forest at the point 0, 0. And you know what you're putting there? You're putting one of these, right? One of these pulleys. So it'll draw a little pulley wheel. The copper mine is at the point 0, 122. So say that's about that, it's about that, it's about right here. So draw a little pulley here. This is the point 0 over 122 centimeters up, and that represents the copper mine, so copper. Okay. And then where's the town? The town is at this coordinate, 122 centimeters over, 61 centimeters up. Okay. So that is right about here. Here's the town at the coordinate 122 centimeters over, 61 centimeters up. Okay. Now, I chose these numbers because I think this is something that your brain might be able to digest because it's a pretty straightforward example. See how these are spaced like an equilateral triangle? You see that? If the transportation costs also happen to be the same, then when you tie 3 strings together and then hang the same equal lab weight over each pulley, then I can tell you exactly where the equilibrium point will land. It will land right here. This is going to be where the factory goes. And this is the coordinate, 35 centimeters over, actually it's 35.2 if you get it really precise, and 61 centimeters up. So the strings would go like this, string, string, string. Of course, you got lab weights hanging over the edge, lab weight, lab weight, lab weight. Okay. You guys get that? How's it working? Questions so far? All right, so that's my example setup. Oh, and one more thing I want to point out is that since this is like an equilateral type triangle, all these angles are 120 degrees each, so it ends up being a per type system. Okay. Scenario A, I did give you guys some transportation costs, but that's all I gave you. So I said, well, let's suppose maybe it's really expensive to transport wood because there's a lot more wood in the pencil than there is copper, so that's part of the factor. And then I don't know, maybe these are numbers, just make up something, right? Okay, so figure out where you want to locate each of these things. And then of course the final location is the factory, right? So the factory has some coordinates. Okay? And then scenario B, I left completely open, so correct whatever you want. I said I put several names on a lab paper, and we've got that mental health thing going today too, don't we? So let me see how much time I should give you guys. 26. All right, okay. Okay, here's how we do this. I'm gonna give you guys about 15 minutes or so to do this, which is not enough time to do this. Also, there's the backside, which ignore it. It's not there. It's not there. That does not exist. I did not show you guys that. So there's definitely not enough time to do this today, but do as much as you can. Hold on to this paper. We might return to this next week. I need to plan next week. So I'll give you guys 15 minutes, and I will walk around, help you guys out. In the meantime, I'm going to leave this example diagram on the projection for you guys.